So this is the second part of the photoelectric effect, in which we are explaining that is known as the stopping voltage. So the first part was the theory, and then we will stay a bit in graphing on the photoelectric. Yeah. So as I mentioned, Einstein was a very theoretical physicist. So he was able to explain theoretically. However, Millikan designed the experiment that was able to prove the theory that, or verify the Einstein's theory, or the theory that Einstein presented. So what Millikan did, he set up an experiment that would allow him to measure the energy of the escaping electron, which varies from metal to metal. We said that. So what is happening is that we are striking the plate that has that special metal here. We are striking the plate with a specific light that we know that will escape the electrons to reach the other plates. However, what we are doing is we are applying an opposite electric field between the two plates to make the electrons not reach the other plate. Okay, so this is known as the stopping voltage. So now, Millikan could make the other electrode so negative that it would repel the photoelectron and prevent them from reaching the other plate. The electric potential established would have the same kinetic energy that the electrons have, because remember what we said in terms of the explanation that Einstein gave for the photoelectric effect is based on the conservation law of energy, which was saying that the energy of the photon is equal to the work function plus the kinetic energy of the electron. So this is what it makes the electron to move from one plate to the other. Therefore, the kinetic energy that the electrons will have has to be opposed by the electric potential energy between the two plates. Then this electric potential energy between the two plates, which we know based on the forces and fields that it is equal to charge times the voltage, difference of voltage, which now is stopping the electrons, and he calls this the stopping voltage. Millikan now had a practical way to measure the energy of the photoelectron by raising the voltage until the current across the tube, the vacuum tube here, across the vacuum tube will stop flowing. In this way, he can measure very accurate value of the kinetic energy of the photoelectron for different frequency of the incident light. Millikan noted that Einstein equation has the same structure as the general equation of the straight line. So remember what we said, that the kinetic energy of the electron is equal to the energy of the photon minus the work function. So for a specific metal, then the kinetic energy of the electron will be H times F minus that work function that is specific for the metal that you are wearing the plate. So this is the same as saying Y is equal to mx plus b, where m is the Planck's constant. X is in the frequency, so what is the frequency? And B is the y-intercept, which now is the has a negative value, and y will be the kinetic energy of the electron. So the graph that we represent this relationship will be something like this. Kinetic energy of the electrons, and in the x-axis we will have the frequency. So then the graph will be a straight line in which the y-intercept is the threshold frequency, and x-intercept is the threshold frequency, y-intercept is the work function, and the slope of this line will be equals to the Planck's constant. When Millikan plotted his data, he found that the slope was indeed the Planck's constant. Also, he found that y-intercept was the metal's work function, and the x-intercept was the threshold frequency. And when he changed the different metals into the plate, into this plate here, when he changed the different metals into this plate, then he noticed that the line was parallel to each other. So the lines were parallel to each other. Or this one here. So therefore they had the same slope. Okay, so this is the threshold frequency for this one. This is the threshold frequency for this one. This is a work function for this specific metal. This is a work function for that specific metal. Millikan's work on a photoelectric effect, along with the Millikan soil drop experiment, led him to awarding another Nobel Prize in physics. Okay, so let's see another example now. If the stopping voltage in a certain photoelectric effect, if the stopping voltage, so stop, is 12 volts, and the incident wavelength of light is 100 nanometers. What is the work function of this metal? Okay. So now, when we know the stopping voltage, what do we know is actually we do have a clue of what the kinetic energy of the electrons is. Why? Because the stopping voltage is making the electrons to not reach the other plate, which means that it is telling us what is the electric potential energy between the two plates to be opposing the kinetic energy of the electrons. So in the conservation law of energy, to explain the photoelectric effect, which is telling us that the kinetic energy of the electrons is equal to the energy of the photons minus the work function, we can say that the kinetic energy of the electrons, when we know the stopping voltage, is Q times the stopping voltage, and the wavelength, or so knowing the wavelength of the light, then we will know what is the energy of the photon as hc over lambda minus work function. From here we can find that work function is equal to hc over lambda minus stopping voltage. And for our information, we have that work is equal to 4.14, and we can say that, yeah, what is it in electronvolts? 4.14 times 10 to the power of negative 15 times 3.0 times 10 to the power of 8 over the wavelength, which is 100 nanometers, times 10 to the power of negative 9 minus 1 electron volt times the stopping voltage was 12. So the work function in your calculator, enter these values on your calculator, you will find that it is, I have 0.42 electron volts, and if they are asking for the joules, then you multiply it by 1.6 times 10 to the power of negative 19, and you will have 6.72 times 10 to the power of negative 20 joules. Now, every metal will have its own work function, and there are different. So starting from aluminum that has about 4.2425, and it goes to potassium that has a 0.59 or 0.60, something like that. So it's unique electron volts. So based on the value that this, if you have a table based on the value of the work function, you can figure out what kind of metal you are working with. Now, what I suggest you doing is work on photoelectric effect online activity. I will post all this information in Google Classroom, and then you can see and complete the information. The goal of this activity is to see visually the effect of changing the frequency, changing the intensity, and then to graphically determine the threshold frequency, work function, and Planck's constant for several metals using the photoelectric effect simulation through PhET. Okay, and this will be the all the information for it will be posted on Google Classroom.